Welcome to a deep dive into the metallurgical anatomy of the final drive. In this video, we'll decode how wear and contamination are revealed through ASTM-D5185 oil analysis. Heavy machinery relies on robust diagnostics, and understanding the final drive's metal profile is crucial for predicting failures and optimizing maintenance. By examining oil samples, we can trace the subtle signatures of component wear, contamination, and even the effects of shared oil system. Let's begin by exploring why the final drive is the ultimate link in the powertrain and how its unique metallurgy shapes its diagnostic fingerprint. Final drive is the last stage in the powertrain, where hydraulic motor speed is reduced to multiply torque for heavy-duty movement. With reduction ratios from 140 to 180, a large bulldozer's final drive can deliver over 150,000 newton-meters of continuous torque per track. This immense force is essential for moving massive loads, but it also means the components inside are under constant stress. Understanding the mechanics and metallurgy here is the first step to decoding oil analysis results and predicting component life. At the heart of the final drive are planetary gears, engineered for continuous heavy load. These gears are made from case-hardened steels with a tough core and a surface hardness of HRC 5862. This design ensures durability under stress but also makes them the primary source of iron Fe in oil analysis. When wear occurs, iron particles are released, providing a clear diagnostic signal. Knowing the alloy composition, such as SAE 8620 with nearly 97% iron, helps us interpret oil analysis data and distinguish between normal and abnormal wear. Let's look closer at the SAE 8620 alloy profile, a standard for planetary gears. This alloy is composed of about 96.8% iron with small additions of chromium, nickel, and molybdenum. Each element plays a role. Iron provides strength, chromium adds surface hardness, nickel increases toughness, and molybdenum improves wear resistance. When oil analysis detects elevated levels of these metals, it can indicate specific gear wear or alloy breakdown, guiding targeted maintenance actions. Key diagnostic rule is that the final drive generates significantly more iron per hour than a differential. Alarm thresholds, such as those used in Caterpillar's SOS program, are typically set at 80-100 ppm of iron, or increases greater than 5 ppm per hour. Monitoring these levels helps maintenance teams catch early signs of excessive wear, preventing costly failures and unplanned downtime. Understanding these benchmarks is essential for interpreting oil analysis reports accurately. Nickel content in gear alloys increases with the need for extreme toughness, especially in larger equipment. By tracking nickel levels in oil analysis, we can infer not only the alloy type but also the operational demands placed on the machine. Higher nickel readings often point to wear in components designed for heavy-duty service, helping pinpoint the source of metal particles and guiding maintenance priorities. Tapered roller bearings are among the most failure-prone components in the final drive, due to constant load and oil contamination risks. These bearings rely on chromium-rich surfaces for wear resistance. When oil analysis detects elevated chromium, it often signals bearing wear. Monitoring chromium levels helps anticipate bearing failures before they escalate, allowing for timely intervention and reduced downtime. Copper dominates the bushings in the final drive, but when the same oil is shared with the hydraulic motor, interpreting oil analysis becomes more complex. Shared oil systems can mix wear signatures, making it harder to pinpoint the exact source of copper. When copper alarms are triggered, typically above 35-50 ppm, maintenance teams must isolate the chemical signature to avoid unnecessary component disassembly. This highlights the importance of understanding both the machine's design and its lubrication system. When a machine shares oil between the final drive and hydraulic motor, a copper alarm requires careful analysis. It's essential to distinguish whether the copper comes from bushings or other components. Advanced diagnostics use chemical fingerprinting to isolate the source, ensuring that maintenance targets the right part. This approach prevents unnecessary repairs and keeps equipment running efficiently. Final drive's housing is made from nodular iron GGG 5060, an alloy with about 92% iron, 3.5% carbon, 2.4% silicon, and a trace of magnesium. Magnesium is a key marker for housing wear. If oil analysis shows elevated magnesium, iron, and silicon, it may indicate cavitation, corrosion, or structural impact. Recognizing these markers helps maintenance teams address root causes before major failures occur. Floating seal or dew cone is made from extremely hard cast iron. Unlike other components, a failing seal doesn't warn with metal particles but rather with environmental ingress. Elevated silicon over 15 ppm signals dirt or silica, while sodium over 20 ppm indicates water or humidity. Monitoring these elements in oil analysis helps detect seal failures early, protecting the final drive from contamination. Oil analysis algorithms visualize metals as geometric polygons, with each alloy forming a unique shape in the ICP-OES spectrometer. These elemental fingerprints allow for rapid identification of wear sources and alloy types. By comparing the shapes, technicians can quickly spot deviations from normal patterns, making diagnostics more efficient and reliable. Gear steels produce distinctive elemental fingerprints in oil analysis. By examining the geometric patterns of iron, chromium, nickel, and other elements, technicians can confirm the presence and condition of gear materials. This method enhances the accuracy of diagnostics, ensuring that maintenance is based on precise, real-time data rather than guesswork. Additional fingerprint patterns from oil analysis provide further insight into the health of gear steels and other components. Each unique polygon corresponds to a specific alloy or wear condition. By building a library of these patterns, maintenance teams can quickly match new samples to known issues, streamlining the diagnostic process and improving reliability. As we continue to explore fingerprint patterns, we see how oil analysis can differentiate between normal wear, early-stage failure, and severe damage. These visual cues are invaluable for proactive maintenance, allowing teams to act before minor issues become major breakdowns. The ability to interpret these patterns is a key skill for modern machinery diagnostics. D5185 oil analysis data tells a sequential story of machine health. By tracking changes in metal content and contamination markers over time, technicians can map out the progression of wear and contamination events. This cascade of data provides early warnings, helping prevent catastrophic failures and extending equipment life. Reverse reading panel translates spectrometer data back to real-world iron levels. This process connects abstract data with tangible machine conditions, making diagnostics actionable. By understanding how spectrometer readings correlate with actual wear, maintenance teams can make informed decisions and prioritize repairs effectively. Final Drive's chemical signature stands apart from other components due to its extreme load regime. Compared to engines, transmissions, and hydraulics, the Final Drive tolerates higher alarm thresholds and requires unique analytical standards. Understanding these differences is vital for accurate diagnostics and effective maintenance planning. Comparative look at metal profiles across engine, manual transmission, hydraulics, and Final Drive reveals distinct patterns. For example, chromium is high in bearings, magnesium is a marker for housings, and nickel is prominent in heavy-duty steels. Recognizing these patterns helps isolate wear sources and improves the precision of oil analysis diagnostics. Because the Final Drive operates under extreme loads, its alarm thresholds and analytical tolerances are set higher than for other components. This ensures that maintenance actions are only triggered by truly abnormal conditions, avoiding unnecessary interventions. Understanding these unique thresholds is key to effective predictive maintenance in heavy machinery. Summary: mastering oil analysis for the Final Drive requires a deep understanding of metallurgy, machine design, and diagnostic thresholds. By decoding the elemental fingerprints and contamination markers, maintenance teams can anticipate failures, optimize service intervals, and extend equipment life. The insights gained from ASTM D5185 analysis empower technicians to make data-driven decisions, ensuring heavy machinery operates at peak performance. Stay tuned for more advanced diagnostics and practical tips in future episodes.